this. Welcome to my workshop toolbox for reverse engineering and binary exploitation. Um, like a bit about me. I was a system administrator at the McGill Genome Center for like 11 years. Then I joined the ethic team at Desjardins in 2016. At first, I did infrastructure testing, then application testing, and now I'm doing vulnerability research in IoT devices. Um, so those are the challenge I had in pace engagements, how I could emulate a single code block or single function instead of a whole binary, or how I could search. Let's say I have a function and I'm doing static analysis, and that function receive arguments. I could sort of guess the arguments I must supply to that function so the program will work. Um, and sometimes I don't even have access to the physical device. So I have like access to the firmware that runs on the device, but I must run it on my computer. And the last problem. Oh, you want more volume? Is it better? All right. And the last challenge was how to emulate an entire device because sometimes you're working on, let's say, the web server of a device, but the web server won't initialize fully unless it has some backend services that are running because it needs to communicate with them. So it's not sufficient to emulate a single binary. You need to emulate the whole thing. So here are the goals of the workshop. The idea is you transfer enough knowledge so you have basic knowledge of the tools, and you'll know like where to look if you want to gain more advanced knowledge of these tools. We'll look at like how to use them and what are the limitations of these tools and how to overcome them. So these are the tools we'll look at today, mostly of Anger, because Anger is the tool that has a steepest learning curve. Then we'll go to Unicorn, then to Chilling, and then at the time, if we have time, a quick overview of QEMU and Renode. But won't do a QEMU and Renode exercise in this workshop. Like that'll be next year workshop. So first, we need to set up the Docker container. Ooh. Okay, still working. So you need to go to the GitHub repository there. I'm not sure if you can read it at the back. It's github.com, then my name, Marc-André Labonté, and then workshop 2024 toolbox. So you need to clone with the recur submodule part. The reason is we'll do a few exercises that I pull from the Anger CTF. So the Anger CTF is a submodule of this workshop. So you need to pull those challenge as well. And on your computer, you'll need to install the Docker engine. So I use Debian. So on Debian is apt install docker.io. If you have another operating system, it's how to you to figure out how to install the Docker engine. And then, since on my machine, I run everything in a VM, so I have to use a proxy server so Docker can pull the images. If you run directly on the host, you don't need to set up the proxy, but I put the instruction to set it up if ever you need it. If you don't, you just skip the proxy instructions. And at the end, you do Docker build with these options. I'll make it better. So you do a Docker build dash dash rm dash dash tag workshop 2024 and then dot. So pick up the Docker file that should be in the when you git clone, it should be in the workshop directory. Um, yeah, and at last, if the build is successful, you should be able to do a Docker run with the dash it dash dash rm and the dash p option with port 8888 will forward the port 8888 on your local host to port 8888 inside the Docker container. And this is for you to access the Jupyter web server. So Jupyter looks like this. Uh, so in Jupyter, you'll have access to all the exercise, the script, even the solution are there, and the C code for the challenge that I made myself. So we'll do most of the workshop in the Jupyter environment. Yeah, might have an issue because I will need both ends to do it, and cannot hold the microphone at the same time. Will be interesting. So I guess you all have the Docker build command running. So it should take about 10 minutes to build a Docker container. So in the meantime, we'll cover the anger theory. And then once you're ready, we'll start with the exercise. So does any of you have issue with the Docker build command, or everyone is building right now? You don't hear me? All right. Do you hear me better? Yeah, it will be harder because I'll need to both of my hand on the keyboard at some point, so I'll have to let go of the microphone and then pick it back up. We'll see how it goes. But at the back now, you can hear me. Okay, perfect. So so you should be building. Should take 10 minutes, and we'll go to anger in the meantime. So the anger, what it does, it can ingest any binary. It support like a lot of architecture. So I use it with x86, with ARM, RISC. It's like I don't know which exactly architecture it supports and which one it doesn't, but most main one you're likely to encounter, Anger will support it. Then it will translate that machine code into an intermediate language, so the rest of Anger can work with the intermediate language. So we'll take your x86 or ARM and translate it in a language that it knows how to use. And then we use a form of emulation called symbolic execution. So symbolic execution allows the Anger to treat the program really as math, and it can use the solver on it. The solver, it will use a constraint. So the constraint you set, it's like you want to Anger to reach a certain point of the program, or Anger to keep running until a register, specific register, has a certain value. So those are the constraints. And like at the end, the constraint solver, if it can succeed, then you'll have like at least one state with the input that you want. If it cannot reach a solution, then it will just raise an exception and bail out. Um, so this image, I took it from the Angular blog post. Is an illustration of the life cycle. So this is the part that translate in the intermediate language. This is the execution and engine with the symbolic execution take place. Then the solver can use this, and also it provide the emulation for file system. So you can use std out, std in, or you can use file with Anger as well. So like I said, the symbolic execution. So when you set the machine state at the beginning, you tell Anger, let's say you want to go at this address. You can tell Anger you start at this address, and you can also give it a list of address to avoid. Like for example, if you're doing a crack me kind of challenge, you said you want to reach the address where the flag is getting printed, and you want to avoid addresses where the program will fail or exit early. So you give it, and then it will start playing with input, like with the symbolic execution. You have certain input that you can tag as symbolic. So that means that Anger can play with those input and see if it, while playing with those input, if it can satisfy all the constraint that you gave it to. So you define the constraint for the solver. Um, we'll see a practical example. Uh, it's like this is really math, but it doesn't have to be maths. Like Anger can use its solver on binaries that are not necessarily doing math operation, but this is a easy example. It's like you can solve it like by hand easily. Um, so you have an input x, and this mathematic equation that is done using the input x, and if the output has a certain value, let's say 35, will print correct answer. If not, it will print try again. So this is like a basic crack me challenge. So then since x is our input and we want to know for which values of x, because if the program is more complicated, Anger can have like more than one state that will reach a solution. So it can be several input that will solve all the constraint. If you have like too many, then you can add more constraint to restrict the quantity of input that will yield a solution. But in this specific case, there's only one value of x that will satisfy the constraint that we set. So we want to go to the printf which what this one correct answer address, and we want to tell Anger to avoid the other address, and the address where it prints try again, want to avoid that. And at the end, when it reach a solution, we want to recover the input because we mark it at symbolic. So when we reach a solution, we need to concretize the symbolic value, which is like get the actual number. So we know the input we were searching for. So when it reaches a solution, there is the eval eval method that we can call and get the x equal 4 value. So what we could do now is do the first exercise and go through the anger script step by step. Uh, so at this point, to do the exercise, you should have the Jupyter environment running. Did the Docker build command succeed? Uh, it's like raise n if it succeeded. So it need more. It need a bit more time. So in the meantime, what we'll do is first you'll have to install Ghidorah, which is like quickly install, or if you have like IDA, binary ninjas, like any reversing tool of choice, you can open the Anger Easy Mat in the your in Ghidra or in your reversing tool. So we'll do it. It takes a bit on my computer. It's a slow machine. Come on, Ghidra, you can do it. All right, and it's the first time that I run it, so I have like okay. So in Ghidra, we need to create a new project first. So let's name it workshop. And in workshop, we do file, import file, and we go in toolbox, anger, and we open the easy mat binary. So it should detect it at the ELF file with the x86 64-bit architecture. So it's most regular one. All right. And then once it's imported, we double click on it to load the binary in what Ghidra called the code browser. So here's our code browser. It will ask if you want to analyze the binary. Most of the time, you just click yes, I want to analyze it, and use the default options. So it should analyze quickly enough. And then I suggest you go in the window and click on functions to display the functions. It's a pretty simple binary. So in the list of function, you just select the main function. And then here on the bottom, you should have like the decompiler tab. So you click the decompiler, and then the function that we are interested in is the solve function. So you will notice the argument passed in the solve function. It's static, and it will make it so that the program will print try again all the time. So the way that I build it, the program will fail every single time. So your goal is like you have a crack me, and you want to figure out an input that will make the program succeed, so you can patch that executable, so change the argument of the sold function so it will print correct answer instead of try again. So if we go back to the main function, damn it, function main. So like by default it passes 32, so 0x20, so 20x. So of course 32 won't satisfy the mathematical equation, and it will fail. So now we should be ready to look at the script in Jupyter. So raise your hand if you have like your Docker container ready to go. So yeah, a lot more people. Perhaps we will wait like 3 more minutes. So I will I will go around and see if anyone is stuck, and 13:30 will do the exercise. All right, 10:30. Um, we'll go in the Jupyter. Uh, so to get to the Jupyter Web UI, what you need to do is when you do the Docker run, it should show you links with the token. I'll make it larger on screen. So I use the HTTP with the localhost colon 8888/lab token equals something. So you right click, copy address, then you go in your browser, open a new tab, and just paste the address. And once you do it, Jupyter should come up. All right. So you should go into the anger folder. You double click on it, and then there's a script called easymat.py. Just double click to open it. So we shall see easymap. I'll try again to make the fonts larger. This should be large enough. And also what you can do, you go back to the launcher tab and you can open a terminal. So it should open a new tab with a pretty good web shell. So it works like a regular shell, but over the web. It's great. I want that web shell in another project. So if you do ls on it, you will be able, it's like you're in a Python virtual environment with all the tools installed. So if you want to run the script, you use the Python command and then the name of the script. So that'll go like this: Python easymat.py, and we'll do it this way for each of the exercise. So use the web shell to run your script and use the building sort of editor to do the challenges. They are mostly like the challenges found on the Anger CTF. They are like filling the blank. So this script, EasyMath, I think you can run it and it will give you the solution right away. But in most of the exercise, I just replace some data or some instruction with a question mark, just like they do in the Anger CTF. So you have to figure out what to put in place of those question marks. So let's see that EasyMath script step by step. So first, we set up the machine state. Anger can support file format, so you can give it the entire ELF binary. Did I see a question? Oh, okay. So you use the project method with the path of the binary when you want to load the binary. We'll see later how to run load a piece of code, because sometimes you don't have like a full binary. You'll only want to load a piece of code. So here I use the print command on project loaders to make sure that the address that Anger will use for its emulation is the same address that you have in Ghidra. And it's like, now it's really small, but we see that Ghidra loads at it's like a 100,000 x the program, and Anger use 400,000 x. So they don't use the same addresses. So if I let's say put address here it will be the address of the solve function. So if I put the address from Ghidra, which is 101.139 here as start address, but my Anger simulation engine wants to use 4,000, then it will just won't work. It won't be able to reach a solution. So what we need to do you can use the print command on project.loader. So Anger will tell you the address that it's using. And then you can set the base address in Ghidra or any reversing tool that you use. So to set this in Ghidra, you have like sort of dim memory icon on top. So you click on it, and then there's a little house icon. So it's meant to set the base address of a binary. So we click on the house, and then we like 4 with 50. So 40000. So 4,000 in hex. 400,000 in hex. And now I have the address of my solve function is now the same that I set in Anger. So any question about the start address and the loader address so far? No, it's fine. Perfect. Perfect. So back on the easymat.py script. So what? Question? Uh, all right. So it's like we are first we need to set the entire machine state. So the initial state where we want Anger to start, and sometime we need to set input at symbolic. So the input we do set as symbolic is the one we want Anger to find for us, and some other time we need to set some memory or register value as concrete values. So those are constant. One example is when you load just a chunk of code, let's say a code block, and you don't have an ELF file, then you need to set the instruction pointer and the stack pointer, so the code will actually be emulated in Anger. So if you have a, let's say, a PE file or ELF file, then Anger will figure these out for you. But if you don't have such a file, then you set them manually. So in our case, we are looking for the x value. So we define a symbolic variable, which is done with clarify.bvs, and we give it a name of x, and we give it a size in bits. So since we're working with the integer, it has like 32-bit value, but you need to figure this out. It's like how large it is in bits from static analysis. And we know that our first argument in x64 Linux binary will be passed in the RDI register. So once we define a symbolic value and we use x as variable name, then we load x in the RDI register, and in the program, it's like the binary will pull that value from that register. Where is it? Here. So Anger will be able to use this. Now, once it's done, we use the simulation manager and set the initial state. Now that we can pass the initial states once we set everything, and then we have to define where we want anger to go and where we want anger not to go. And is in this example, we pull the standard output and we do a compare with the data we are getting from standard output and the string that we saw from the static analysis. So we tell Anger, if you ever see correct answer in the standard output, then you know that you reach your destination. So it's one constraint that we are giving to Anger, and if it reach that, then Anger will know that it solved the constraint. Of course, you can add more constraint, but that's the first one we need to set here. And the second one is addresses we want to avoid. So we want Anger not to go to try again. So Anger will play with input, and if there is any condition like a compare, like an if statement, so it will have like a branch. Let's say if some value is greater or equal than 1, then go this way, and if it's 0 or less, then keep going. So Anger will create two state to keep track of execution going on each side. So at the end, if a state reach, it's like if a state make it so that try again gets written in standard output, then it will be discarded because we tell Anger to discard such a state. What question? Yeah, it's done automatically, and my guess will be at each instruction. We'll see up later when we'll do the automatic exploit generation. Um, the way we do it is we tell Anger to go one step. It's like here we tell the simulation manager to just keep going until it's reach the correct answer. But when we do exploit generation, we just we tell it to go one step, then check if some register is now symbolic. So Anger should do that internally. It's like go one step, then check everything, go another step. So it takes a while, though. It makes emulation in Anger slower than, let's say, in Unicorn or QEMU or other emulation tools. And we'll have a good example of that later on. Um, so here we actually start the simulation manager, so the emulation, and we tell it to check that function. And if it returns true, it means that destination has been reached. And the avoid, you can pass it a function or a list of addresses, and Anger will discard the state if this is true. Um, so at the end, if Anger can reach the destination that we set, then this will get called simulation.found, and we'll have a table of Anger state that we're able to like solve these constraints. So here we should have only one state, but in a crack me, you can have like more than one. So here we just pick up the first state in that table. And then, as I said earlier, we need to concretize symbolic input. So we have a state that satisfies the constraint. So we want Tellinger which input that you set that created this state. So we use the eval method, uh, and then we know that the variable we want to concretize is x, and we want to make it an integer. And in some cases, it will be a string, so we cast to bytes and we decode the string. And then we print the integer. So we should be ready to try it. So let's go in the web shell and let's hope for the best. It takes a few seconds. Mm, all right. So yeah, you'll see warning about some memory and register that were used and that we did not set up properly in our initial state. So we'll say that in this case, we can either tell Anger to zero fill those memory addresses and those register that we didn't explicitly set, or we can also tell Anger to make them symbolic. I think if I remember correctly, I'm not 100% sure, but if I remember correctly, by default, Anger will set any of register that you didn't set it in your initial state as symbolic. But we did not concretize them. We don't care. We just care about the value of x in this case. So you should have at the end solution found patch binary. So solve argument is equal to 4. So, were you successful in running that script? Ah, excellent. So let's go back to the slides. Uh, so we covered this part, and all right. Next challenge will be a challenge pulled from the Anger CTF, filing the GitHub repo of that CTF. It's a pretty good one to get to learn Anger. I will suggest you try all these challenges. We'll do 3 of those challenges in the workshop today. So we'll go back to Jupyter and load in the Anger CTF folder, in the this folder, the scaffold 03.py. So back to Jupyter here, and we'll close this tab, go Anger CTF, this, and scaffold 03. And at the same time, we need to load the binary file, which is in the same folder. It's called 03 Anger Symbolic Register. So we load it in Ghidra. So we go back to Ghidra again. Close this. Uh, So directly from the code browser, you could import the file and open it. So we click on File, Import. Then we go Anger CTF, this, and O3 Anger Symbolic Register, and import. Should be detected as x86 32 bits. So this one is a really old binary. It's not 64, it's 32. And I'm not sure it has like PIE. So yes, want to analyze it. Analyze, again, default options. Uh, so here we should see the main function. And basically we'll print enter password, then I will run the get user input function, then we'll run a few functions, complex 1, 2, 3, and then check some condition, print good job if everything is equal to 0, otherwise print try again. So all right, let's try it. Uh, so these are the question mark I told you about. So perhaps I'll let you a few minutes, let's say 5 minutes to do it, and I'll do it. I'll do it as well, and then we check if everything goes as we planned. So, uh, any of you did finish the scaffold O3? Oh, it's like, nah, it failed my side as well, so I'll fix it. Yeah, something I can figure out quite yet. Uh, do you have any questions? Yeah, I guess I'm having issue with the hanger loader address. So perhaps we might need to change the base address in that challenge as well. We'll do it. All right. Thanks to him. Now I fix up my own script. Okay. So at the end, you should have like three values, and you should convert them in hexadecimal. Because if you look at the get user input function, um, they use the um, percentage X format specifier. So it's meant that the user input will be converted in hexadecimal numbers. So you need when you enter your password inside the program, you need to enter it as a hexadecimal number. And also, as Anger doesn't support emulation of scanf with several inputs, then you need to skip it. So you need to start execution in function main and right after get user input return. So if you go here, I suggest you start the execution at 8048980. So that should be your start address. And let's go back to Juniper. If you want to test it, you should be able to run the executable and then you should add like enter the password prompt. Then whoop, you copy and paste values. Wait a bit. And yeah, you can check if the value that Anger came up with allow you to really run the program and get good job written on screen. So a few of you have already succeeded, and time is going on, so we need to get moving to the next challenge. So, right, let's talk about. We talk a bit about that, but let's talk again about state creation. So, let's say you are in GDB, you're doing like step, 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 and each time you're checking the machine state, you're checking the stack, checking the register, and then you encounter a branch. So you have an if branch. So sometime at some input value, the program go one way, and some other time go the other way. So then you need to explore both paths. So when doing it manually with step, 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 it takes a long while. And also you can only, as a human, explore a single path at a time, at once. So let's say, what if you could duplicate yourself like Agent Smith in Matrix? So you have like the two of you, and then you explore the path in parallel. Anger lets you just do that. So if Anger encounters a branch, it will create two states and explore both paths at the same time. But there is an issue with this. So let's say you have like a for loop, and within that for loop, you have a branch or several branch. Then at each iteration, it will explore the double. It's like the states that are exploring paths will double at each iteration. So let's look at this example. Yes, this check could be optimized out of the loop, but that's not the point. So let's say you have a check that you must be doing inside the loop, and it's like the first time you do it, it will create two states, and the second time, second iteration, each state will go through the loop again and create two more states. So doubling the amount of state Anger has to keep track of, and the loop will go over like 4,000 times. So what will happen here is the machine will just crawl to a halt, and the CPU fan will be running. So fortunately, there are ways to avoid being getting bogged down by state explosion. We call that state explosion. So that leads us to a second Anger CTF challenge, which teach us how to deal with this. So let's open the challenge 08 in Ghidra. So again, file, import, and pick up 08. And yes, analyze it. Okay, so let's also open it in Jupyter. Uh, uh, so again, let's take a few minutes to do the exercise, and we'll cover it at 12:25, at 14:25. Sorry. All right. Uh, did anyone got a solution for the challenge 8 in the Anger CTF? Should get a string, and we'll see if I got the right string. So I'll test my own solution right now, and then we'll go into the script, and I'll explain it bit per bit. Yeah, it worked. So let's see what was happening here. Um, basically, well, tell us that if you try to go into that function check equals with anger, then wait, I thought you then you'll get a state explosion. So you need to avoid going into the check equal function in anger. So what you will do instead is you'll stop right before the check equals function, and you'll tell anger, since it gives you it's like a string, and you know that the input that you send is being processed, and then at the end is being compared with that specific string. So you need to tell Anger um, here is the input you start with, the buffer you start with. So you mark it as symbolic. So you tell Anger to play with that buffer and to find um, some input data that once processed will be equal to the string that the program is set to compare with, and the string is encoded in the function name to help us a bit. So when we start at the beginning of the script, uh, we need to tell Anger where to start, and again, we want to avoid going into the scanf function. So I'm telling Anger to start like right after the call to the scanf function. And then we need to tell Anger the input it has to work with. So the size of the input here is in bits. So it's like mind the size, because when you set the constraint at the end, the size will be in bytes. So here we know that the input is 16 bytes. So I use 16 times 8 to tell Anger the size in bit in our symbolic variable. And then we need to tell Anger at which address the scanf data will be stored. And locally, it's a static address. So if you click on the buffer here, you'll see it's stored at 0804A050. So you set that address, and then you store it in memory in your initial state. And you also set in your initial state the address you want Anger to reach. So you don't want Anger to reach good job or try again directly, because you don't want to go into the check equal function. So you set the destination address right before the call to the check equal function. So it will be 804.8673. And you start the simulation manager, and it should find a solution, because the only constraint you gave so far to the simulation manager is reach that specific address, and Anger should reach it easily, so it will find a solution. But then you want to load the symbolic value and add an additional constraint. So you want Anger not only to reach that address, but to play with the buffer, the scanf input data, in such a way that once processed, when it reached the destination address, the content at that memory location will be equals to this string. So that means that in its input buffer, it has the correct password. So you add the second constraint this way. So the data you pull from memory when you reach the solution here is equal to the desired value here. And then to get the actual data, you need to go to the concretize step. So you convert the symbolic value to concrete value. So you do it again. You do it with eval, and uh, what you want to get is the password variable you set at the beginning, and you want to convert data to bytes, and then you can just print the byte array, and it should print as a string. So, any question about that exercise so far? Yes. It's from static analysis. So it gives you a lot of clue in the beginning of the script if you read the command. And also here, it's encoded in the function name. So of course, when you're playing with real binary, um, might be harder to figure out. Yeah. Yeah, there is a check, and you want to check to return through. What you might be able to do is to use unicorn to go through that function. But in this case, they are helping us a lot by giving us the string we need to compare against. In real life, you might not get it. So let's move on to next exercise. So anger, sometime like we saw, we need to avoid some function, and most of the time we would like to avoid going into standard library code. And so fortunately, we can uh, either skip or emulate it as a sim procedure mechanism to emulate standard library code. So we'll treat it as a single instruction and won't go through it with the simulation manager. So there is an exercise about that. It's the CTF challenge, Anger CTF challenge number 10, where we use sim procedure. It's like and here there is also challenge number 9, which has uh, some things that will help you get it. It's like you can copy, you can look at challenge number 9 at the same time and copy this comparison from it to help you solve challenge number 10. So the end afterward will go to automatic exploit generation. Let's have like 10 minutes to solve that challenge. Yeah, it's it's here in the script. When you define the function that will replace the library function. So you define the hook. Uh, the return value suggests you copy the code from the slide. This code here, that goes here in the return clarify.if with the value. You can just use the code here. Yeah. One quick note for challenge number 10. You need to pull STD in to get the solution. So you need to concretize standard input. All right. Whoop, sorry, I am entangled in the wire. All right. Raise your hand if you could solve the challenge 10 from the Anger CTF. Oh, yeah, the guys at the back is machine. Great. um, so we'll look at it. So the idea, let's go in Ghidra. You remember last challenge, we want to avoid going into a function because if anger will go into it, will suffer a state explosion and won't be able to reach a solution. So the way that challenge approach the problem is instead of avoiding that function, then we just redo it. So we are telling anger that instead of using the check function, uh, we define a replacement function. So yeah, they call the class replacement check equals um, to replace the check equals function. And in the run method, we can receive the argument. So those, it always receives self, and those argument, we get them from static analysis. So if we look at Ghidra here, oh, sorry. Yeah, wait, okay. If we look at Ghidra, the check equals function receive an address. It's local 25, and uh, local 25 will be populated by scanf, so will come from standard input. So that's why at the end we need to concretize standard input. So our first argument is the address of the input buffer. And the second argument, we could figure out it will be the length of the input because, again, they help us a lot and they gave us the reference string, which is 16 byte long. So we have 0x10, so 16 in hexadecimal as input length. So since from static analysis we know that we receive two arguments, then we give them whatever name we want. So the first argument here is the address of our input buffer, and the second one is the length. Uh, so we set them in those variable, and we can do the comparison in Python inside that function. So we load that address, and um, we check against that string, and we return a concrete value of 1 if it's true, and a concrete value of 0 if it's false. So that's how to return a boolean in anger. And then we set our simulation manager. So we had the hook here. So we tell simulation manager not to go through the check equal function and use our replacement check equal instead. And like the previous challenge, we check standard output to see if we reach the right destination or if we should discard the state. And then that is the part I had to look up is we concretize the standard input file at the end to get the input value that will make the check input succeed. So if you run this, you should get a string, and when you run the binary, and you input that string, it should print. Good job. Yeah, thanks for attending. So, any questions so far about this part? All right. So we go on to the most interesting part, the part that will hopefully give you points tonight. So the automatic exploit generation. So yes, you can use Anger to write memory corruption exploit for you. We'll use buffer overflows as example, but it does not necessarily have to be buffer overflows. So the idea is we get the simulation manager to keep going, so we don't specify a destination address, but we make it step, and then we check the machine state, and we mark some input as symbolic as usual. But each step, when we check the machine state, we check if, let's say, the program counter register is also symbolic. Because if it becomes symbolic at one step, that means that Anger can control it using the input. That means that Anger really took over the control flow of the program. But yeah, you can check a register, or you can check also memory bugs by looking at memory address if it's becoming symbolic or not. So the way it works is we use Radar 2. Radar 2 is already installed inside the Docker container. So we use Radar 2 to analyze the binary, and we get the address of the vulnerable function from Radar 2. Then we feed Anger the address of the vulnerable function. Then we use a static hooker to automatically hook all C library function. So again, we want to avoid the simulation manager to go through those. And then we step through the vulnerable function, and for each step we check if the PC register for, so it's like different architecture can use different register name from for the program counter, but in Anger it will pretty much always be called PC for program counter. Oops, sorry. uh, And then it's like we can also add a constraint to make sure that the program counter has a specific value that we chose. So let's say, okay, keep going until the program counter is equal to a, or something like that, any value that we chose. So then we make sure we really control the program counter. And at last, we use pawn tools to build our RUP chain to really exploit the program. So the first example that I've made myself is called Pawn Me Maybe. So again, let's open the Pawn Me Maybe Py script in Jupyter and the Pawn Me Maybe binary in Ghidra. So here, go in the EAG folder and open the Pawn Me Maybe script. And we open the binary in Ghidra. So I'll go in the script in detail, so you get to know how it works. And then we will do one exercise, which will be the NorthSec 2023 surveillance.ctf track, but the last challenge of that track, uh, which was using pretty much this exact script. So let's go in Ghidra. Let's import anger, AG, and Pon Me maybe. So it's statically compiled, so there's a lot of functions. So we'll search for the main function, and we look at the main function, and what we see is it reads from standard input. So it's file number 0, which is a standard input, and uh, it will write it in the buffer 118, which is like 264 byte wide, and it tries to write like 2000 bytes in it. So of course the buffer will overflow. But the idea here is we want to reach a function that will not be executed normally. So we want to reach that function. So we'll do a wrap chain that will call we want to go there function. So let's look at the script. So the first function will check if the data that we supply to it is symbolic or not. So that's our way to check if the PC register is symbolic. Because at the beginning of the program, it should not be, because it will be defined by the ELF loader. So it's concrete at start. It's not symbolic. So here we build our wrap chain. And yeah, the first step is we use R2 pipe to load the program into radar and control radar from our Python script. Then we look for the main function, which in which our buffer overflow lies, and we get the address of that function, and we supply the address to Anger, and then we tell Anger to use the static hooker, so it won't go through libc functions. And we set up our simulation manager, and it's here that we go and through we step in the simulation manager, and for each step we check the machine state to see if Anger has control of the PC register. So we check if PC register is symbolic or not. And then if it becomes symbolic, it means that we found our solution. So we found an exploitable state, and then we add a constraint to make sure we can really set the PC register from the standard input. But it could be like, and in the NorthSec 2023 was really a network input. So you send a message to the program over the network, and then you'll overflow a buffer. It doesn't have to be always standard input, although we use that in most example. No. All right. So if we run that script from the command line, Should take a bit. And if it succeeds, the script will dump the actual payload, which is like the padding to fill the buffer. Then it will override the return address, and after that, it will put the RUP chain and dump everything in the payload file. So create a file which is called payload, and then to test the exploit, you just run the binary and cat that payload file into the standard input. So if we run this, yeah, of course it will crash, but it will go through that. We want to go there function and print the flag. So we took over the execution of the program, and let's say there's a system function loaded somewhere. We could divert the execution flow to run that function. That should not run normally. So that was our goal, and maybe the program crashed after, but we did our deeds. So the next challenge, if we go back to the slide, uh, next challenge will be surveillance.ctf last challenge. So the way it works at NorthSec 2023 is you will receive a camera firmware over some web service, and you had like 1 minute to analyze them and exploit them. So that was not possible to solve any of these challenges manually analyzing binary with Ghidra. So the challenge designer wanted us to come up with automatic analysis and exploitation. And the last challenge, you had to automatically exploit a buffer overflow that is really similar to the one that I wrote as an exercise. So you could look northsec23.py in Jupyter. Oh, and I did not solve the challenge in time, I must admit, but was motivated by this particular challenge to create this workshop you're attending. So let's load this. Yeah, unfortunately, I think I did make a mistake, and I did not add the question mark into the NorthSec 2023.py script. So it should work right away. Oops. What question? Yeah, yeah. The solutions. If you want the solutions to the challenge, there is a solution folder in Anger, and also I think in EG also I have a solution folder. Oh, I've solved that by. So I have like the original challenge designer script to solve it. And if you want to see the solutions for any of the Anger CTF challenge, You go in Anger CTF, the solution folder, and I have, if we go in Anger CTF, I have the solution folder for the three challenge that we pull from the Anger CTF. But in the NorthSec 2023 case, should be solve.py here. But the script NorthSec 2023 should be almost ready to solve it. Let's try it. Je sais pourquoi que autres les question mark. Moi j'ai une ancienne version. Pas la dernière version de mon blog. C'est quelque chose que j'ai changé dans. Yeah, my machine is a bit slow. So again, if the NorthSec 2023 script is successful, it will it will create a payload file in the current working directory, and then you feed it to the program to see if we could exploit it. And what the RUP chain will try to do in this case, if we look at the RUP chain, is it will search, it will open a file called secret in the current working directory. It will expect the file descriptor to be 3, and it will read 100 bytes from that file, and it will write that data to standard output. So that's how in that challenge you will get the flag. The flag was stored in a file called secret on the server. And if I remember, they gave you that as a hint. And so you had to write a RUP chain to, once you took over the program, to read the secret file and have the content of the secret file sent back to you over the network. But fortunately, will work on the command line as well. So if we try it, yeah, it's it's called deactivating. Deactivation pin is not stored in a file called secret. I need to create a file called secret first. Sorry. Now I have a file called secret. So let's see if I can read it with my exploit. Yay, it worked. So I received the content of the file called secret on standard output. So any question about those challenges? Were you able to make them work on your computer mostly? Like I guess I'll be able available if you have any question like later on. Now we'll go back to the slide. We'll try unicorn challenge because like time is going. So I'll go over to unicorn. So unicorn is a CPU emulator. So it support again many architecture, and it's like it will allow you to emulate uh, call block function or even an entire executable. But there is a catch. Unicorn doesn't support things like system calls, and also it doesn't have like ELF loader. So we can have a quick look about the example that is pulled from the unicorn tutorial. It's very, very simple. All it does is it writes um, constant in some register. So if we quickly run it, go back, unicorn, and it's example one. So in Unicorn, you need to set the entire machine state. So you need to define a section in memory. At least you need to define executable section and the stack. That's the very least you need these two. But depending on the code you're trying to emulate, you might need more. Uh, Here we define the machine as x86 32 bits. Um, we create a memory address to host the code that we'll be emulating. And this is our actual code. So we'll be writing these number into these registers. And then we will display the values in the register just to check if our emulation was working. So let's run it. Yeah. So we see quickly see the results. So we'll try a case, more complicated case. Again, Unicorn also support hooking, just like Anger, and the chilling tool we'll see after also support hooking. And you can also trace all instruction. It's very useful for debugging. So let's say you work in GDB and you do step, you check the machine state, you do step again. It's like Unicorn can do it for you, and you can see the machine state flowing. It's like you can automated all the work you used to do in a debugger like GDB. And I made a challenge that is using both Anger and Unicorn. So I'll do this one. This one is a good one, and then we'll do maybe the if time allow. We'll do the HP ILO one. So the HP ILO is it's like a real life challenge. It's like I really had to do analysis on that thing. HP ILO is a baseboard management controller, so it's meant to allow a system administrator to remotely manage servers. And of course, it's an entire different computer. It doesn't even use the same architecture of the host server. The server is x86, but the ILO daughterboard is using ARM 32-bit. So those old, this is an old one. Generation 3 is end of life. So no 0 day here. But yeah, it's a different computer embedded in the server, and usually it is connected to the network. So that's something that you will want to test. So in this exercise, we'll see how to decompress the ILO firmware to start analyzing it, because that those now they are encrypted, so you have to decrypt on top of the compressing. But those older firmware, they were not encrypted, so you only had to do the decompression. So we'll do the previous challenge first. So the obfuscation challenge. So the obfuscation challenge, you'll see in some device, in some binary, the manufacturer will try to hide some things. So I took that as an example. Let's say it doesn't have like clear text string in the memory. In the binary, it will have like encrypted strings. And let's say you manage to obtain the decryption function. So the obfuscation bin file is not even a ELF executable. It's a single function that I took from ELF binary, then I dumped to disk. So it's a bit harder to analyze with Ghidra, but it's on purpose. And also give you a good hint is the first 4 byte of the plain text. Once it becomes a known plain text attack, the first 4 byte are F, L, A, and G in capital. So uppercase flag. So let's load the binary and the script. So loading in Ghidra will be a bit different because we're dealing with a raw binary. It's not ELF again, so there's no executable file header. So we need to tell Ghidra which architecture, Indianness, and bit size to use. So again, we go back into Ghidra and we file, import, and we'll do unicorn and obfuscation.bin. And we use the 3 dot icon just next to the language input box to specify architecture. So it's ARM V8 32-bit Little Endian. So the compiler field, choose the default one, not the Visual Studio one. So you should have like a dialog box like this one with language ARM LE, which stands for Little Indian V8 and default. And then it should load. And uh, so there is no main function here. Uh, so we click on the reset function. The reset function just means that we are telling Ghidra to start the decompiler really at the beginning of the file, because the file, it's like I I compile the file and then I select the bytecode of a specific function, then I dump that bytecode to disk. So you have to tell Ghidra, please start the decompiler at offset 0 of that file. So in the function list, you just select the reset function, and then you should have like the decryption function. So if you look at it, it takes two parameters, 1 and 2, and you see it does a bit shift on the second parameter, and on the first parameter, it goes through a loop, and it does write to it at a certain offset. Ustack C will see what it does, and it takes input from that table, which is populated by the second parameter, and it will XOR with a byte and the first parameter at that same offset. So first parameter like kind of look like a string, and the second one perhaps looks like a key. And this function here, if you try to double click to go to it, it doesn't exist. So we will have to use hooks in Unicorn to re-implement it. And we have to sort of figure out what it does. And it's like it runs on parameter 1, which might look like a string, and it returns a value. Then our index here is compared against that value. So that while loop will run until index is equal to the return value here. So to me, looks like strlen. So it measure the length of the ciphertext. And again, that function was used to actually display the plain text printed, but it doesn't exist. Although what we could do is we could again hook it or read the memory just right before this call and just write our own printf in Unicorn as well. So let's load the Unicorn exercise in Jupyter. Uh, okay. I'll close a couple of tabs. And should be called deobfuscation.py. So if we look at it together, I'll like a function to display the machine state. So it's to help debugging. So again, you can have it step through the code, and at each step automatically display the machine state. And then we load the ciphertext. And here we will use both Anger and Unicorn. We use Anger to brute force the key. So we know that the first 4 bytes is uppercase F, A, F, L, A, and G. And we will set the input as the key input as symbolic, and have anger run through the loop the first 4 times, and set a constraint on telling her like play with the second parameter, but find a state that'll make it so the output, so the string that we're getting at the end, start with FLANG. And we don't use anger to try this decipher the whole thing, because it takes too much time. It will enter the state explosion problem. So we do the first 4 times with anger to get the key. And then by looking at the code, we know that the key is being reused. So to decipher the entire ciphertext, we can use a unicorn to emulate the loop, and it will go much faster than anger will do. So here, since we don't have a ELF file, we need to load and set everything in memory. So I picked up 10,000X as a start address. So you could even like set 0 here, because by default in Ghidra, so we do the opposite at the beginning of the workshop. We we set the base address in Ghidra, or we could do that. You choose. So you can set the base address in Ghidra to match the script, or you can set the base address in the script to match the default in Ghidra, which is 0. So let's say I will match Ghidra, so I will set the base address as 0, entry point as 0, start address again 0. And then we need to create a stack. We need to set the link register, so setting the machine state. And then we need to create a symbolic value that will be our key. So let's call it key. So since we are doing ARM, the key is the second parameter. So according to the calling convention, it will be passed in the register R0. So we load our symbolic key value into register R0. R1, sorry, R1, since it's the second parameter, not the first one. So it's R1. So here that is our first parameter. So that is the ciphertext. So the ciphertext, we really need to load it at R0. So here we we are defining our skip string loop. Again, we want here a string length to return 4, since we only want to reiterate through the loop 4 times with anger. And then we go on to the unicorn part. I wrote a few helpful function for debugging unicorn. This is called hook code. So it's a function that will display the machine state and even automatically disassemble the code for us. And these function fetch unmap is a hook that will help you if the code that we're running is accessing unexpected memory addresses. Then you can also debug it. That means that when you set the machine state at the beginning, then you need to map more memory, or you need to map memory at these addresses, so the actual emulation can take place. And here that hook printf function, it's my own Python implementation of printf, so it will do the printf for us. So we need to load the binary, and it should be obfuscation.bin. So we'll go through the unicorn machine state part, and then if we run the if we run the deobfuscate.py script, you should see we'll get the key, then use that key to decipher the entire plain text. And perhaps I'll go through the conclusion afterwards. So here, um, we start the unicorn machine state. Uh, you need again to load the same binary and to use the same address as you use in Anger. So I decided to use address 0 because that's the one I had in Ghidra. But you can pick up any address. So we load the file, then we create the stack. So we need to map memory for the stack, and we initialize the stack pointer. We initialize also a few basic register like link register on ARM and the frame pointer. And then we need to load in memory both the ciphertext and the key. And we add our hooks. So we need to hook the string length function and the printf function. And you see I commented the hook code, but if you remove that command, you'll get to see the machine state and the disassembly at each step. So you can use it for debugging, but if you go through a loop with tracing enabled, it will be really, really, really slow. And for the next challenge, if you try it, the high-low challenge, the decompression loop is a bit long to execute. It will take like 45 seconds if you emulate with Unicorn. But if you have like tracing enable and you go through the firmware decompression loop, it will take forever. It's like I tried it and I just gave up. I hit Control C. So at last, you tell Unicorn the start address. So start address will be 0 in our case. And we also tell it the address that we want to reach. So we want to stop execution right before the last the function call 7A14, which again doesn't exist. So we stop execution right before that function call, and then we just read the data from the input. So the R0 register, the first argument, which should contain our plain text, we just read it with our printf hook. So the end address will be 0xD8. So it's D8 in X away from your start address. So here in the hanger constraint solving part, we were we had as an int that the first 4 character are FLAG uppercase. So we just set that as the constraint parameter desired value. And we can look here that we're pulling from register R1 4 byte to compare against that desired value. So that R1 register is our key. So we want Anger to find a key that when we send the ciphertext into that function, the first 4 byte of the plain text will be flagged. And that's about it. Let's try and run that script. Invalid syntax. Sorry. Yeah, the script failed because I forgot to put the file name, um, so to tell Anger which file to load. Uh, and then again, I need to tell that's unicorn where to hook string length. So I need to specify those addresses as well. All right. Um, anyone could solve the deobfuscation challenge? Yeah, I guess it's a was a bit hard. Like next workshop, I'll make it like tiny bit easier. Let's go again to the conclusion. So I suggest even you try the challenge like by yourself over time. Uh, it's not that hard, but yeah, maybe it takes more than 3 hours. Here the high-low challenge. You have like the get high-low.sh script that will pull it for you because I couldn't include that piece of software into my repo. Uh, we'll skip over it. The chilling. Chilling is also it's like unicorn. I think even it uses unicorn, but it also emulates an entire operating system. So over unicorn, it has like several advantages. It can take care of library loads, and system calls. And you can also use hooking just like the previous tool in Anger and Unicorn. I gave some link for a few good demos of chilling, like for malware analysis. It's like getting a payload from a dropper, also UEFI emulation, and to emulate a native library. And there's also a chilling CTF that you could try to learn it. It's like the exercise I'm providing is called TCP Vuln. So again, it's a real life challenge. And it's like I had a device to analyze, and I found a buffer overflow in a login function. Uh, so it's like I had to load I wasn't able to emulate the web server, so I had to load that library inside that binary called TCP-vol, which will implement a basic web server. So obviously that code isn't provided, so you won't see which device, but you could see that you could write a skeleton web server to load a library, vulnerable library from a web server running on a device you do research on. So if you try TCP vuln, if you try to emulate it using Unicorn, it will fail at the socket system call because Unicorn emulates just a CPU, so it cannot handle system call, which is a way to tell from user space to tell the kernel to do things for us. So they use a specific instruction, the CPU. But if Unicorn encounters such instruction like the service instruction on ARM, it will just fail. So you have to use chilling to do this. So if you try with Unicorn, will fail at socket. But if you try with chilling, you'll be able to reach the HTTP auth function, which is not there. But you can write your own vulnerable HTTP auth. Again, you have a limitation in chilling. The limitation I encountered was I had to emulate, let's say, web server, and that web server depend on other services that was running on the device. But Unicorn can only emulate a single binary at a time, and that binary, the web server, won't initialize, so it won't be usable and reachable from the network if those services weren't running, and it was like too complicated to patch the web server so it will run without these services. So what I came up with instead is I use QEMU and system emulation. So the way I made it work is I use a framework called BuildRoot to build my own kernel, and I try to build a kernel that is similar as possible to the kernel that is on the device I'm working on. And I will extract the root file system from that device and emulate the whole thing on QEMU, and it did work. And what another tool that you can use for that purpose is called Renode. Renode will make a good workshop in itself. Renode, you start with a bus, and then you can define memory map peripheral. So there is a thing which is called a flattened device tree. which when you work on the device, you can extract it from the flash memory. So it's a binary file which tell which device, let's say a SPI controller, UART, is mapped and where in memory. So you can take that and tell Renode, hey Renode, I want that UART controller emulated and mapped like there in memory. And you take the data from the device you're studying and you're populating your Renode virtual machine with the same memory map devices. And then, if all goes well, you could run your kernel that you extracted from the device inside the Renode virtual machine. So yeah, thank you for staying to the end.